Good morning, everyone. We are about to start with the first talk of the day. Unfortunately, Stefano Bruno cannot be with us to deliver this talk, but fortunately, Ying has kindly offered to give this talk for us. Thank you very much, Ying. It is about diffusion-based generative models. We have the log-concave case here, but we have some interesting calculations when it comes to numerics and some explicit estimations for both optimization and sampling. Okay, so Ying, the floor is yours. Thank you so much.
Thank you for the introduction, Sotiris, and also thank you for all the effort in organizing this event. As said by Sotiris, in fact, Stefano was supposed to give the talk, but he couldn't join, and I borrowed the slides from Stefano. So I'm going to speak about on diffusion-based generative models and their error bound. And as you can see from the title, I will talk about the full convergence estimates for diffusion models. And basically, I will explain how we obtain the estimates that connects the sampling procedure and the optimization procedure in diffusion models. This talk is based on the joint work with Stefano, Denise, Dongyang, and Sotiris. So we're considering the following question. It's again the same question. We are given a set of data points. These data points are distributed according to some unknown distribution, we denoted by pi d. And now the task is how do we generate new samples also from this distribution pi d? And as discussed in the first week by Arnold and Valentine, that in literature there are many ways, VAE and energy-based methods, but here we focus on the very popular diffusion-based or the score-based generative modeling. And this is a picture from the paper by Song et al. So basically the procedure, so there are two procedures. So the first procedure is to sequentially corrupt the data set with slowly increasing noise. So at the end of the day, we have some simple noise, Gaussian noise. This is the first step. And in the second step, we reverse this process. We want to remove the noise injected into the original data. And so as to form a generative model of the data and to obtain new samples. This type of concept is first introduced in the paper by Song Dinkelstein et al. In 2015, and then made popular by Song and Ermo et al. These papers. It has been really successful because the application of this type of models has achieved state-of-the-art results in many applications. And these are the examples, including the image generation and audio generation, as well as recently this protein design. And here are all the relevant literature. And here I'm going to speak again this type of example, which is the text-to-image task. And in all these softwares, Image and DALI-3, Stable Diffusion, all these softwares, the diffusion-based generative models play a key role, and they're able to generate really high-quality pictures. Now the question is that despite this really successful and great empirical performance, the understanding of the diffusion models, its mathematical underpinnings is still limited. But we see recently there are a lot of results about the convergence of the diffusion models. And our focus here is to provide a full theoretical guarantees that links the two procedures, the sampling procedure and the optimization procedure. in the diffusion models. I'm going to briefly talk about the theoretical background of the diffusion models so that we are on the same page regarding the notation and the setting. In diffusion models, like I described here, we want to corrupt the data with noise. And here what we do is that we diffuse the data with this forward Ornstein-Uhlenbeck process. And we denote it by xt. It is governed by this type of Longevin SD with the drift being minus x, and the diffusion is a constant matrix. And its starting point is an unknown distribution pi d, and we denote by m the distribution of the dimension of the data distribution. And we denote by we diffuse the data using this type of forward SD. And then in the second step, because we want to remove the noise, and what we do is that we want to consider the time reversal of the OU process. And according to the results by Anderson, Hausman, Perdue, Conforti et al., as well as the paper by Annie, we know that the backward process of the OU, the forward process can have this form, this SDE. So we denote by YT the backward or the time reversal of the OU process, and it has this type of drift, y plus 2 times gradient log p capital T minus TYT, and it has a constant diffusion. And its starting point is exactly the law of x capital T. In this SDE, we denote by PT the family of densities of the law of xt with respect to the Lebesgue measure. And crucially here, this driving Brownian motion is something that is independent of BT, which is the Brownian motion for the forward process. And under some conditions on the coefficient of the forward process, this backward time reversal has needs some weak solution. So we want to use the backward procedure to generate new samples, but in practice, what we do is that instead of starting from this law of xt, we start from the Gaussian noise because the law of xt is usually unknown, and it is also much easier to sample directly from the standard Gaussian distribution. And secondly, this score function related to the forward process is intractable and cannot be really computed explicitly. So here we want to use some approximating function to approximate this score. And this corresponds to the optimization procedure involved in the diffusion models. Thirdly, because we want to generate samples, we want to consider numerical schemes that tracks the solution of the backward process. And for example, we can use the Euler-Maruyama scheme or the very popular exponential integrator scheme. So, but this introduced the discretization error. And so to sum up, these three modifications, I would say, give rise to the three types of errors. The first one is the initialization error, and the second one is the approximation error, and the third one is the discretization error, and the third one also relates to the sampling procedure in the model. So I'm going to talk about the optimization procedure and then the sampling procedure, and then we will see a motivating example that links these two procedures. So the question is, how do we approximate the score function? And so here we denote by S the approximating function, and we consider this type of score matching, that is to minimize in theta this objective function. Basically, it's an L2 error between the true score function and the approximating function S. And in practice, we slightly modify this type of objective function, and we involve this weighting function denoted by kappa. So now the objective function becomes this integral of this kappa divided by t minus epsilon and then multiplied by, again, this integral. Here, this epsilon is some constant greater than 0 and is this early stopping thing, because according to my understanding, in this type of optimization procedure, in some cases, if without introducing this early stopping, the objective function is not well defined, is infinite when t tends to 0. So here, what we want to do is that we really want to find an estimator theta hat, which is an estimator of the true minimizer of the objective function u, which can be obtained through some approximation procedure. For example, through some optimization algorithms. To make life easier, we consider this denoising score matching, which is a very nice observation documented in this Vincent paper. So we have this objective function, and by calculations, we can rewrite it as this expectation plus some constant. The important thing is that this constant is independent of theta, and this is good in the sense that when we want to find an estimator of the minimizer through some approximation procedure, we want to, for example, use the gradient descent type of algorithm. When we calculate the stochastic gradient of this type of objective function, then we can completely throw this part away because it's independent of theta. Let me introduce the notation in this expectation here. So this tau is some random variable that is uniformly distributed on epsilon to t. Epsilon is the constant greater than 0. And this z is normally distributed, and mt and sigma t has this type of expression. So now we want to minimize this objective function, and its associated stochastic gradient has this type of expression. The x here is a vector of t, x0, and z, and its dimension is 2 capital M plus 1. This capital M is the dimension of the data distribution. Now this is the optimization procedure. So, and we want to consider the sampling procedure. So it is basically the backward process of the diffusion models. So for the backward process, we have recall that we have this YT, which is exactly the time reversal of the OU process, and it has this expression that we have just seen. And we denote by YT2 then the backward process, but with the initial distribution replaced with the standard Gaussian, and everything else, this SD is the same as YT. Now, crucially, in our work, we introduced this novel process we denoted by YOXT, and this process is simply this YT with the score function replaced with this approximated score. And here, instead of just theta, we have theta hat. This means that it can be obtained, it can be just some output from optimization algorithm. So we want to discretize this auxiliary process using Euler-Maruyama approximation. And here is the expression. For this Euler scheme, we have the step size denoted by gamma. And we denote by this Z bar some standard Gaussian random vector. To facilitate the analysis, we also introduce continuous time interpolation of the Euler-Maruyama scheme. And this continuous time interpolation is denoted by this y hat EMT. And the thing is that the continuous time interpolation coincides with the original scheme at these grid points. So these are the processes that are involved in the sampling procedure of the diffusion models. So our goal is to establish the convergence result in Wasserstein 2 distance. That is, we want to find an upper bound for this quantity. The reason that we want to consider the Wasserstein 2 distance from theoretical point of view, because it connects to the strong L2 arrow, and we have tools from stochastic analysis to upper bound this type of distance. And from practical point of view, as Antonio has discussed on Tuesday, because Wasserstein distance is relatively less computationally expensive to compute. And additionally, also we have this threshold inception distance that is exactly the Wasserstein 2 distance between the distribution of the generated images and with the distribution of the true images. So the lower the score, the greater the sample variety. So this gives these reasons give motivation to consider the Wasserstein 2 distance. And now I will show you this motivating example where we really provide full theoretical guarantees for the diffusion models that connects both procedures. In this example, we consider the very basic case where the unknown distribution is just standard, it's just a Gaussian with an unknown parameter, with the unknown mean. Here, this parameter is mu and it's in RD. For this specific example, we're able to compute explicitly the score function. So it is given by minus x plus mt mu. So here we have explicit expression, but mu is unknown. Now, because we have this expression and we can choose our approximating functions to approximate it, and this s, we choose it to be minus x plus mt theta. And we want to find an estimator. So now we have this approximating function, and we observe that the true minimizer of the objective function is exactly when theta star equals to mu, right? When theta is mu and we have zero error. So we want to use some optimization procedure to really find an estimator of this optimizer. Then what we do is that we plug back this expression into the optimization problem, into the objective function. And there we choose, because we have the weighting function here, and we choose this weighting function kappa to be sigma t squared, as in the paper by Song and Ermo. So as a result, after calculations, we can see that in this case, with this specific case and the specific choice of kappa, everything is well defined when epsilon is 0. So we don't need this early stopping in the optimization procedure, neither in the sampling procedure. And we can have a simplified expression for the stochastic gradient associated with the optimization procedure. So it is given here. And we may observe that from this stochastic gradient that it is linear in theta. And we can also show that it is, in fact, it satisfies the strong convexity condition. Therefore, so for this motivating example, we choose the SGLD algorithm to optimize the objective function. So to be more precise, the SGLD algorithm is given here. It starts from theta naught, some initial value, and the updating rule is given here. For this SGLD algorithm, lambda is its step size. This should not be confused with the step size for the Euler-Maruyama scheme in the backward process. So we have lambda to be the step size of the SGLD algorithm, and Kc is the sequence of standard Gaussian random vectors, and beta is the inverse temperature current. Now here, for the stochastic gradient, this xn is a sequence of IID data points. So in order to generate this xn, what we do is that because it's a vector of these three random variables, what we do is that we sample Ln from the uniform distribution non-zero to capital T, such that the law of Ln is the law of tau. And then we sample this x0n from the data set, available data set that is from pi d. It's not directly from pi d. And then such that the law of x0n is the law of x0. And thirdly, we just sample the Zn from standard Gaussian distribution such that the law of Zn is the law of Z. Then we can show that by doing this, we can show that the stochastic gradient is in fact the unbiased estimator of the exact gradient of the objective function. We further impose the condition that theta 0, Kc and xn are independent. Then, given the fact that we can calculate and we can prove that H is strongly convex, in fact, H is satisfies some convexity condition, and then if you do the calculation, you will see that when you take expectation, the exact gradient is strongly convex. So we have this type of conditions in the paper by Keegan et al. And the main result in the paper is that if we have this type of condition and the stochastic gradient satisfies certain type of convexity condition for large enough beta, the output of this SGLD algorithm is an almost minimizer of U when n is large. So by this result, we can set theta hat just to be the nth output of the SGLD algorithm. And then we have that the true score function is approximately just the approximating function S evaluated at this theta hat. Here, this theta hat, we just set it to be the nth iteration of SGLD algorithm. And this n should be large. Now for the result for the motivating example, it's given here. So for any beta greater than 0, there exists constant such that for any Tn and lambda, which is the step size of the SGLD algorithm within this range, and for any gamma, which is the step size for the Euler-Maruyama process in the backward, which approximates the backward dynamic, with gamma in this range 0 to 1/2. We have this type of upper bound for the law of the backward scheme and the underlying distribution pi d in Wasserstein 2 distance. We have this type of upper bound. So these three terms on the right-hand side of this result corresponds to the three types of error that I mentioned previously. more precisely, for the first term, it corresponds to the initialization error. And for yes,
I forgot what is gamma, small gamma.
it's the step size of the order. Yeah, exactly. And for the second term on the right-hand side, it corresponds to the corresponds to the approximation error, because we approximate the true score. So it corresponds to that error. And for the third term, it corresponds to the discretization error. The discretization error, of course, it contains some other terms, but basically is this term. So the key thing here is that first, the constants on the upper bound, this CSGLD 1 and 2, as well as this step size restriction, these are explicit. Then if we look at the dependence on the key parameter, for example, on the dimension, it is for the square root of b, which is optimal. And we also obtain the optimal rate of convergence for the sampling algorithm as well as for the optimization algorithm. For the sampling algorithm, the optimal rate of convergence is gamma. This is a classical result because the Euler scheme coincides with the Milstein scheme when the diffusion is constant. So we have this rate. And for the optimization algorithm, we have shown that the optimal rate of convergence is square root of lambda. So for this example, we have achieved the optimal results in each of these aspects. And this also means that we can, for any given precision level delta, we can choose sequentially capital T, beta, lambda, n, and gamma explicitly to make this bound, this upper bound arbitrarily small. Or in other words, we can choose these parameters explicitly so that the law of the scheme, the Euler scheme, is absolutely close to the underlying distribution in Wasserstein 2 distance. So this is the result for the motivating example where we really link the sampling problem with the optimization problem. Now we want to consider more general setting. And in this more general setting, first of all, we do not specify the optimization algorithm, and therefore we would need to impose some conditions on the optimization algorithm. So the assumption says that we would assume that the noisy score matching, this optimization problem, this objective function has a minimizer, theta star. And if we denote by theta hat the estimator of this theta star, which can be obtained through some approximation procedure, we require it to have finite fourth moment. And this is usually finite second moment would suffice, but here we require fourth moment because we want to obtain the optimal rate for the sampling procedure. Then we assume that there exists some constant such that this L2 error between the estimator and the minimizer is controlled by this arbitrary small value. And this is in fact satisfied in the motivating example, right? Because for the SGLD algorithm, under this type of stochastic gradient, we have this result that shows that by choosing the parameters gamma and beta, these parameters, we can make this error arbitrarily small. And this assumption just allows you to choose whatever algorithm that that converges, basically. Then in the second assumption, we impose conditions on the data distribution, but because in general case, we do not assume that the underlying distribution has certain form. So for the data distribution, we assume that it has a finite second moment to make sense of the upper bound. And we assume that it is strongly log-concave. And we also impose this type of integrability condition. So the data distribution being strongly log-concave could translate to this type of condition on the score function. And this integrability condition together with this type of condition will ensure the existence of the unique strong solution of the backward process YT, the time reverse of the OU process, as well as this Y tilde process, that is the time reversal with the initial distribution replaced with the Gaussian. So these conditions will ensure the unique strong solution of these two processes. And then we just note that because here we have this type of constant that is dependent on time. So in our analysis, we just consider a uniform lower bound to ease the notation. So next, because now we do not specify the expression of the approximating function, so we would need to impose some conditions. And basically, this assumption says that I would assume that the approximating function is continuously differentiable in x. And we assume that S satisfies some Lipschitz condition in theta and in x, whereas it satisfies some Holder condition in t. This alpha varies between 1/2 and 1. Then we further assume that the gradient S in x, it satisfies some Lipschitz condition in x. Then the other conditions just, so for the rest of the assumptions, we just impose growth conditions for this coefficient D1, D2, and D3. And we also assume the integrability condition for these functions. And finally, we impose conditions on the score approximation. This is because if we record a motivating example, we have explicit form for the true score and the approximating function. And this explicit expression will translate to the L2 arrow between theta hat and theta star, so that we can control this arrow. But here, because we do not know the explicit form of the true score, neither the approximating function, so it's unclear that how this expression will translate to the distance between theta hat and theta star. So we impose this type of condition. Basically, it says that it exists some constant such that this L2 arrow between the true score and the approximating function is controlled. The thing is that in this assumption, the expectation is taken respect to the known information, is taken with respect to the auxiliary process as well as theta hat. So for auxiliary process, we recall that it has this expression, and everything is known because we know the initial distribution is just a standard Gaussian. We will be able to choose explicitly this approximating function as long as it satisfies this assumption. So this is known, and this theta hat is an output from some optimization procedure, and this is also known. So this expectation is taken with respect to the known information. And we may compare it with some assumptions in previous results where the expectation is taken with respect to the unknown density PT. So here is our main result in the general case. So this result says that under the assumptions 1 to 4, there exists constant such that for n capital T, gamma, and epsilon, the upper bound will have this type of upper bound for the Wasserstein 2 distance between the law of the scheme and the underlying distribution. So for this upper bound, again, the constant C1 to C4 are explicit. And we have the C4 here that has the dependence on the dimension. So it's the order of M. So M is the dimension of the data distribution. Here we have it, the dependence is M because we want to obtain the optimal rate of convergence for the sampling scheme. So it increases the dependence on the dimension. So if it's the rate of convergence is just 1/2, then I believe here it should be the square root of M. But because we have this type of result, we see that the convergence is gamma to alpha, where alpha is 1/2 to 1. Then when alpha is 1, then this is optimal rate of convergence for the sampling scheme. And so this increases the dependence on the dimension. Then again, for this type of upper bound, we can choose explicitly these constants to make it arbitrarily small. And we have that the law of the scheme is again epsilon close to the pi d to the underlying distribution in Wasserstein 2 distance in this general case. Finally, I will just very briefly talk about the proof. So it basically relies on this type of splitting because we want to obtain an upper bound in Wasserstein 2 distance. And the way we split it is that we use the time reversal of the OU process, and we use this process Y tilde, which is with the standard Gaussian initialization. And we also use this auxiliary process. So we would need to bound each of these terms. So for the first term on the right-hand side, because it's exactly the time reversal of the OU process, and we just the law of the Y capital T minus epsilon is just the law of X epsilon. So here we have that this XT equals to this term, this quantity in distribution. And after the calculation, we can see that it's a simple calculation. It's exactly C1 times square root of epsilon. So to upper bound the second term, here this is basically an SD starting from different initial point. So initial distribution. And here we use the assumptions on the data distribution where basically this strong convexity condition, and this translates to that the score satisfies some one-sided Lipschitz condition. And here we also use the fact that we can write this, we can have this, this write xt in this form, and this holds almost surely. So this ZT comes from the because we can solve the OU process explicitly, and this ZT is some stochastic integral. It's a normalized integral, so that this ZT is normally standard, follows standard normal distribution. We also use the fact that this Y02 that equals to ZT almost surely. Then using this fact, we can obtain this type of upper bound here. Then for the third term, to upper bound it, because now here we have the SDE involving the true score and the approximated score. So we need the assumptions on the score score approximation to upper bound this distance. Here we again use the assumptions on the data distribution where the score satisfies some one-sided Lipschitz condition. And this gives the third term on the right-hand side. Here we see that this term, which appears in this assumption, appears here. So this is the upper bound for the second term. then for the last term is just the numerical, the convergence of the numerical scheme to the SDE. And here, because we want to obtain the optimal rate, we use the trick introduced in this paper by Kuma and Sabanis. And in order to obtain this improved rate, we would need the assumptions on the gradient of S with respect to X, and we need the force moment of theta hat to be finite. And then this gives the upper bound here. Summing up, we obtain this type of result. And here are some constants, and that's all for my talk. Thank you for your attention.
Ying, thank you so much for this wonderful talk. Stefano cannot be with us for reasons out with his control, but I think you did a brilliant job. Although I'm sure you're very tired with the organization of this program, but that was a wonderful talk. Thank you so much. I know Stefano will be happy. Any questions?
Thank you. Very nice talk. For the Gaussian result, in the theorem, I think you had this beta constant or beta parameter. Yes, and can you elaborate what is the role of this beta? And then there is in the second line there is that term d times c1 over beta.
This one?
Yeah. So you want to choose beta large to make that small, but does that make that c constant blow up or not?
Yeah, it's like we will fix beta. So we choose this parameter sequentially. So we first choose b and then we choose beta. Once beta is chosen, so it's fixed.
Can you say what this beta parameter is? Is it in the algorithm or?
Yes, it's in this SGLD of it.
Oh, okay. Sorry, I missed that. Oh, okay. Okay.
Yeah.
I see. Thank you.
Allow me to comment here as well. You know, this is one feature of the Langevin algorithms that we have been highlighting throughout the program. Beta is the inverse temperature. And of course, the typical scenario here is beta is going to be very large. And why is that? Because then you have small contribution from the noise. And then really the SGLD here or the Langevin-based algorithm, we follow the stochastic gradient descent, right? Because if we pay attention, if I'm to hide this term, really we have a stochastic gradient descent there, right? But with the Langevin dynamics, we can achieve more because we have an invariant measure, we have this fantastic toolbox from stochastic analysis. And of course, with Miklos, Eric, and Ying and other collaborators, we did this initial analysis in SGLD. You can see all that there. If you move now to the slide of the estimates, let me highlight this as well. And observe, the great thing is that always beta appears with D in this very nice form. So no matter how big D is, 1 billion, you can choose your beta to be 1 billion. And then you cancel the effect of the dimension, essentially there. Okay, so this is a super nice term. And let me highlight again that the rate of convergence here for the optimization is 1/2. And we know that in stochastic gradient descent with Langevin dynamics. So when we have stochastic gradients, this is an optimal rate. And again, as Ying highlighted, for the numerical approximation, we have rate 1, which is the Milstein scheme. Although we're using essentially the Euler-Maruyama, something very simple, but because of the constant diffusion coefficient, we get something for free, essentially. So these are optimal rates, but this is the, if you like, the very nice case where we have strong concavity, if you like, or for the potential, we have a strongly convex case. So I'm stealing the spotlight now. Apologies. Any other questions? Adrian, I'm expecting a question from you at this point. No. Nothing? Okay. So then maybe I will conclude and say that was an effort, and that's why we focused initially, and of course, Stefano has driven a lot of this, to solve together. You see. But because I started, let me conclude my remark, was to solve together the optimization and the sampling problem, right? Because generative modeling is, or generative models is all about solving the optimization and the sampling together and putting your estimates to see how big your error is, right? Because many times we see that people saying, okay, somehow I solve the optimization and then I move to sampling, or some people say, I don't pay attention to the sampling. I go to only to the optimization part and I do my analysis. So I will say, maybe I will say this, if you go away from the strongly log-concave case, you have to be careful because again, the problem of generative models is a combined problem. So your assumptions have to work for both sets of problems. You cannot close your eyes and say, okay, I do only the sampling. I have these conditions are very nice. And you don't know what is happening in the optimization problem. Because in real life, you have to solve the optimization problem and you have to solve it optimally. Okay, Yusuf.
So a very small question. What is this epsilon? So you have an initial condition, right? And you go to P minus epsilon. If you go to the assumptions.
The early stopping probably.
Yeah. Instead of 0, you have epsilon.
Yes. Yeah. Because here, generally, if we consider, for example, Gaussian with some, if it's not just the identity matrix, it's some sigma t squared, then once you do the calculation, you will see that this term explodes when t close to 0. So usually we have this epsilon early stopping to avoid this problem, to make this optimization problem well defined.
This is well known. This is well known and it's a standard practice in generative models to avoid the explosion, right? Because the score depends on time. And when it goes to 0, sometimes it behaves badly. Not always.
Is that time for more question?
Yeah, of course. We have plenty of time.
So for the Gaussian case, from your result, it looks like the sample complexity is not too bad. The sample complexity meaning, I think little n, right? That's how many new samples you need to train.
Right. This n is this encode. I think it's this one. The number of iterations of this GLD algorithm.
Right. So that's how many samples from the target
It's-
distribution that you need.
Is the how many steps we would need for the optimization algorithm to reach to the approximate minimizers. For the output to be absolutely close to the true minimizer of this mu. So this n is related. This n relates to the optimization procedure.
I see, but is it not also the number of samples that you need from the target?
No. It's so for here for each update, we just need this one sample, 1x, and you can for each time you need this 1x and to run your algorithm. So here is not really the number of samples from the underlying distribution. Here this n is really the number of iterations of the optimization algorithm.
So maybe I can say this.
So basically use only one sample in the batch.
So even we don't use the batch size here, right? So if you pay attention, this is super nice because I think you're referring now to the empirical risk minimization. Whereas here, because the underlying assumption is that we have a Gaussian, things become super nice for us when we run, and this is what they do usually in stochastic approximations. When you run forward the optimization procedure, and you feel now that you are close to the invariant measure, okay, for calculating whatever expectation you want to calculate and get your estimate, you collect the data points from the same path even. But this is just a numerical trick. So to your point, right? Here, because at the end of the day, you have to calculate an expectation, and usually it will be an empirical expectation, right? To do your estimates, you're going to use all the data points that you have, right? If you were to run for each of the data points, the optimization sequence forward to converge.
I see.
Okay, but obviously you can do this batch size, and you can have some saving there as well, instead of using all the data. It's possible because this is the stochastic gradient setting. And when we write H, we give also this option to people, but we hide it, right? Because it's a standard procedure. People know that when you do batch sizes, really you create a stochastic gradient there. And again, it's an unbiased estimator of the original gradient. So the answer is, we do not do the dependence on the number of samples, because there you have to define even further heights, and then you complicate the notation even more. But it will be a straightforward kind of standard calculation, I would say, in this case.
Okay.
Hopefully that answers the question.
Yeah, I think so.
Okay.
Thank you.
Any other questions? Okay, so I think we're good. Let's thank Ying again. Fantastic. Thank you so much.